Welcome back to the Deep Dive, where we dig into the latest research to help you stay ahead. Today, we're tackling something pretty fundamental in advanced AI training. It's this challenge of making sure large language models, the LLMs, actually do what we want them to do, getting them aligned, helpful, harmless, honest. It really depends heavily on something called the reward model. But the usual ways of building these reward models, well, they hit some serious walls, especially with scaling up and getting them to generalize well. But that might be changing. We're diving into a really fascinating paper today. Pre-trained policy discriminators are general reward models. This is by Shihan Du and colleagues from Shanghai AI Laboratory and Fudan University. Seems like a potential game changer.
It really offers a novel perspective, yeah. The core idea is that they redefine what a reward model even is. So instead of just giving like an absolute score for how good an answer is, they frame it as a policy discriminator. What that means is the reward model measures the difference between different ways an AI might behave different policies to create a reward signal. This guides the AI you're training towards a desired target policy. Their method, Polar, that's policy discriminative learning, uses this really scalable pre-training. It learns to spot identical policies and, importantly, tell different ones apart. And this moves beyond just relying on subjective human preferences about what's best. The results are pretty striking. Polar 7B, for example, blows past traditional methods without pre-training, preference accuracy. On STEM tasks, it jumped from around 55% to 81%. That's huge creative writing, up from about 58% to over 85%. And it generalizes well in RLHF too. That's reinforcement learning from human feedback. It boosted models like Lemma 3.18b significantly by about 9 percentage points. And Quen 2.532b saw gains of over 5 points across 20 benchmarks. Plus, they found clear power law scaling. That's always a good sign for future potential.
Wow, okay. That's a really packed summary, thanks. So our mission today is to unpack this whole approach, right? Could mean for, the future of training and aligning these big AI models. I think you'll find this really shifts how we think about reward models, what they are, and what they can actually do. So let's kick off by just reminding ourselves why reinforcement learning is so critical in that post-training phase for LLMs. The whole success of RL and basically the final behavior of the LLM, it really hangs on the reward model giving precise and crucially stable feedback. Without that reliable signal, you're kind of optimizing in the dark, aren't you?
Absolutely. You're flying blind. And that brings up the limitations of the old ways. What's wrong with traditional reward models? Well, first, scalability, big problem. They need tons and tons of high quality human labeled preference pairs. Like, this answer is better than that answer.
Yeah.
Getting that data is slow, it's expensive, it's just hard work. And second, they often don't generalize well. Because they learn subjective human preferences, they can be vulnerable to reward hacking. The model finds a clever shortcut to get a high reward score, but it's not actually doing what the human intended.
Right, like acing the test without learning the material.
Yeah.
I get that. And okay, some might say, what about rule-based verifiers? We use those for coding, maybe logical reasoning.
Yeah, where you have clear rules.
Exactly. They can give you a simple thumbs up or thumbs down. If the code runs, check. If the logic is sound, check. But they really fall down to those open-ended areas, don't they? Like writing a good story or translating poetry. The rules for creativity or nuance are just, well, they're fuzzy, subjective, almost impossible to write down beforehand. It's not just right or wrong.
Exactly. And think about how LLMs themselves got so powerful. They unified all sorts of language tasks under one simple goal: predict the next token. That allowed for incredible generalization. The paper argues we need something similar for reward models, a kind of fundamental criterion-agnostic objective for pre-training, something that doesn't depend on specific human rules for this task or that task. We need a foundational principle, not just a patchwork of specific preferences.
Okay, so that sets the stage. Given those challenges, scalability, generalization, the limits of rules, how does Polar rethink the reward model? What's the core shift?
The big conceptual leap is this: redefining the reward model as a policy discriminator. So forget absolute scores based on human criteria, at least initially. Instead, Polar measures the difference between a candidate policy, how the AI might respond, and a desired target policy. Policies that are more similar to the target naturally get higher scores. It's about relative closeness, not absolute goodness. And the beauty here is it cuts out the need for all those manually defined subjective preferences during pre-training. The objective itself discriminating between policies applies basically anywhere you have policies you want to compare. This makes it inherently scalable and a really fundamental way to pre-train these models.
Let's make that more concrete.
The paper has some great examples. Think about that prompt. How many R's are in strawberry? A traditional reward model might give, say, 0.2 for 2 R's and 0.8 for 3 R's. A rule-based one just gives a check or a cross.
Right.
Simple. But Polar works differently. It uses a reference response. Let's say the reference is perfect. There are 3 R's in the word strawberry. Let me explain. Now, Polar R7B gives an identical answer, a high score, like 0.690. But an answer saying there are 2 R's, it gets slammed with a really low score, like managed in 9.5.
A big negative, yeah.
But here's where it gets nuanced. What about a correct answer, 3 R's, but with slightly different reasoning? Maybe like, let's break down strawberry. Straberry. Count the R's there, 3.
Still gets a negative score, maybe negative 6 point something, but noticeably better than the outright wrong answer.
Exactly. It's closer to the target policy of providing a correct, reasoned answer, even if the text isn't identical. And even a wrong answer, but with correct-looking thoughts, like there are 2 R's, so the answer 3, gets a very low score, but maybe slightly less low than a totally wrong answer with wrong thoughts.
It's really about the difference in the underlying generation process, the policy, not just the final output text.
And this isn't just for factual stuff, right?
Right.
What about creative tasks?
No, it applies there too. Take the Dune summary prompt. Summarize the first book of Frank Herbert's Dune in one witty, short sentence. Okay, to say the references. Royal team discovers that life's a beach minus the ocean, plus spice, giant sandworms, and deadly politics. Identical answer gets a positive score, maybe 0.467. Now, what if a candidate is similar but makes a factual error, like mentions magic instead of spice? It gets penalized heavily, like negative 7.7.
Okay, makes sense.
But here's the cool part. What about a completely different but still witty and accurate summary? Like, young nobles move to desert planet turns into galactic Game of Thrones with fewer dragons, more worms. It still gets negative score relative to the exact reference, maybe a negative 6.9, but that's significantly better than the factually incorrect one. It shows Polar can recognize quality, wit, conciseness, relevance, even when the phrasing is totally different. It's judging alignment with the policy of being witty and summarizing Dune, not just matching words to the reference.
That really clarifies it. It's comparing the underlying how, not just the what's.
Okay, so how do they actually train Polar to do this? You mentioned 2 stages.
Right, a 2-stage paradigm. Stage 1 is unsupervised reward pre-training. This is where the core policy discrimination skill is learned. The goal is purely for the reward model to learn to tell different policies apart and quantify those differences, all without any human label saying this is good or this is bad.
Okay, how?
They create this absolutely massive synthetic data set. They take a huge, diverse pool of existing LLMs, base models, chat models, even intermediate checkpoints like 131 base, 53 chat, 78 checkpoints.
Wow.
And they sample trajectories, prompt response pairs from all of them. This gives you a huge variety of policy examples. The total data set is 3.6 trillion tokens.
Trillion. Okay, that's serious scale. Yeah. Then they use a contrastive learning approach with Bradley-Terry loss. Basically, it learns to push representations of trajectories from different policies apart while pulling representations from the same policy together. It learns to recognize this came from Model A versus this came from Model B, or this also came from Model A. They had practical hurdles, of course, like needing to truncate responses that got stuck in loops, and finding the right sampling temperature 1.0 worked best to get enough variety without making the outputs nonsensical. But the key outcome is the reward model shifts from just judging single answers to measuring this deeper policy differentiation.
Right, so it builds this fundamental understanding of policy space, you could say. But it doesn't yet know what humans prefer, does it?
Yeah.
How does that come in?
That's stage 2. Supervised fine-tuning with human criteria. Now, the goal is to take that pre-trained criterion-agnostic reward model and align it with what humans actually value. This uses a much, much smaller data set, around 150,000 examples. Still significant, but tiny compared to pre-training. Here, for a given prompt, human annotators look at 3 different responses generated by different policies and rank them. Best, middle, worst.
Ah, okay. So now the human preference comes in.
Exactly. This ranking effectively imposes human criteria onto the model. It learns to map its understanding of policy differences onto human judgments of quality. It uses a supervised ranking loss, consistent with the Bradley-Terry stuff from pre-training, and a neat flexibility point. The reference trajectories used here can be human-written, or they can come from really high-performing LLMs. This means you could potentially adapt Polar to new domains or tasks relatively quickly without needing tons of near-human annotation each time.
That adaptability sounds really useful.
Okay.
Okay, this sounds incredibly promising theoretically. Let's get to the results. How well did Polar actually do in practice?
The empirical results are really strong. They trained Polar 1.8b and Polar 7b models. First, looking at preference evaluation, basically, how well the reward model agrees with human judgments about which response is better. Polar significantly outperformed traditional reward models that don't have this pre-training stage. Get this, Polar 7b actually beat the state-of-the-art world PM model, which has 72 billion parameters, so 10 times bigger. Polar 7b was nearly 6 percentage points better on average.
Wow, 10 times smaller, but significantly better. That's impressive.
It really is. And on specific task types, the gains were even bigger. Remember those numbers. STEM accuracy up over 25 points to 81%. Creative writing up almost 30 points to 85.5%. Strong gains in reasoning and chat too. The authors attribute this directly to the pre-training. Learning those nuanced policy differences first gives it really robust generalization, even to things it didn't see explicit preferences for during fine-tuning.
Okay, that's preference evaluation. But you said earlier the real test is RLHF training, right?
Yeah.
How well does it actually guide the LLM being trained?
Exactly, that's the downstream task where it really matters. And here again, Polar RMs consistently did better than traditional ones. For instance, they took Llama 3.18b and fine-tuned it using different reward models. Using Polar R7b as the reward signal boosted its performance across 20 benchmarks by about 9 percentage points compared to the original Llama 3.18b. And crucially, it was also about 6.7 points better than the same Llama model fine-tuned using that big World PM72b reward model.
So the better reward model leads to a better final LLM.
Precisely. Quan 2.532b also saw solid gains, improving by over 5 percentage points when using Polar. Now here's a really interesting detail. In the preference evaluations, Polar R 1.8b and Polar 7b performed pretty similarly. You might think they'd be equally good for RLHF, but in the actual RLHF training, the larger Polar 7b gave a noticeably bigger boost to the final LLM's performance.
So the standard preference test didn't fully capture the downstream impact.
Seems that way. It suggests that maybe our current preference evaluation methods aren't perfectly correlated with how effective a reward model will be in the loop, guiding optimization. The RLHF results might be the truer measure.
That's a really important point for methodology. Okay, another thing you mentioned earlier was scaling laws. That sounds potentially huge. Can you elaborate?
Yeah, this is quite exciting. They found that Polar exhibits clear power law scaling behavior. What that means is there's a predictable mathematical relationship, a power law between how well the model performs, measured by validation loss, and things like the number of parameters in the model or the amount of computation used to train it.
Like we see with the regular LLMs.
Exactly like that. They plotted validation loss against model size and against optimal training compute, and got really clean power law fits with high R-squared values, meaning the fit was very good. The specific equations were L proportional to N 0.0425 for parameters N, and L proportional to C 0.0342 for compute.
Okay, and the implication?
The big implication is predictability and scalability. It strongly suggests that if we just build bigger polar models and train them with more compute, we can expect them to get predictably better. It confirms this isn't some fluke, it's a scalable approach. We likely haven't hit the limits of how good these policy discriminator reward models can get.
That really opens the door for future improvements just by scaling up. Okay, to really nail down why Polar works so well, the researchers did ablation studies, right?
Yeah.
Taking parts away to see what happens.
Exactly. They wanted to isolate the key ingredients.
What did they find? What's the most critical part?
Well, first they looked at the impact of pre-training. They trained models only on the supervised human preference data, stage 2, without doing the massive unsupervised pre-training, stage 1. Interestingly, these fine-tuning only models did okay on the preference evaluation benchmarks. They could learn to mimic human preferences reasonably well. But when used in actual RLHF training to guide an LLM, their performance tanked. There was a substantial drop compared to the full Polar models. This really highlights that the unsupervised pre-training stage, learning those policy differences, is absolutely crucial for generating effective reward signals that lead to good downstream performance and generalization. It's not just about matching static preferences.
Okay, so pre-training is key. What else?
They also looked at the impact of reference trajectories. Remember how Polar uses a reference response? They found that even if you don't do the Polar pre-training, just using reference trajectories during the standard supervised reward model training gives a benefit. Compared to traditional methods that just score responses in isolation, having that reference provides clearer, more stable guidance for the policy being trained. It gives it a target to aim for, essentially.
Makes sense. And one more comparison.
Yeah, they compared reinforcement fine-tuning, RFT, which is what Polar enables, versus just doing supervised fine-tuning, SFT, on the same data. Meaning, instead of using the reward model in an RL loop, just train the LLM directly on the good examples identified by the reward model. They found RFT using Polar was significantly more effective. The RL process really leverages the reward signal more robustly than just imitating the best examples. It shows Polar RMs act as really effective graders, providing accurate signals that the RL algorithm can use to optimize the policy effectively.
Okay, putting it all together then. Polar seems like a genuinely new angle on reward models, thinking of them as policy discriminators. This two-stage training, starting with that massive unsupervised pre-training to learn policy differences, then fine-tuning with human preferences, seems to deliver really impressive results. It outperforms much bigger traditional models, not just on paper in preference evaluations, but crucially in actually improving LLMs during RLHF.
Absolutely, it's a compelling package. But, like any good research, the paper is upfront about limitations and future directions.
Right, what are those?
One obvious one is the reliance on reference trajectories during that second fine-tuning stage. While effective, generating or annotating those references still costs time and money. Future work could look into using multiple references, maybe automatically selecting good ones, or even using references from related but different prompts to reduce that annotation burden. Making it cheaper is key for wider use.
Oh, good point. What else?
Another interesting avenue is integration with test time scaling techniques. Think about things like OpenAI's O-series models, or DeepSeek R1, which do more reasoning at inference time. Could you combine Polar's powerful pre-trained reward modeling with these dynamic inference methods? That could be a potent combination.
Yeah, synergizing training and inference improvements.
And finally, just exploring the scaling potential. Those scaling laws are a huge green light. There's likely a lot more performance to unlock just by training bigger Polar models on more data with more compute. They do caution, though, that generating the pre-training data for Polar sampling from all those diverse policies is computationally much more expensive than standard LLM pre-training data collection. So scaling up has its own challenges. But the potential payoff, given the scaling laws, seems significant. It really suggests these general reward models could become incredibly powerful.
It really does make you think. If Polar's approach scales well, and it acts as this general policy discriminator, well, what are the ultimate limits here? How good can these general reward models get? And how might that fundamentally shift the whole landscape of AI training and alignment down the road? Something to chew on. Well, we hope this deep dive into pre-trained policy discriminators or general reward models has given you a solid grasp of this really innovative work. Thanks for joining us on the deep dive.